Hello, everybody. Thanks for coming to part two. In this talk, I'll tell you about bordered Floer homology, and in particular, bordered Floer homology via immersed curves. And I'll tell you how to use this to detect some fiber patterns, their genus, and some aspects of the monodromy of certain satellites with fiber patterns. To start with, I just want to mention the original version of the pairing theorem, that's Duda, Lipschitz, Osvath, and Thurston. This says that to compute the knot Floer complex of a satellite knot, I can realize that is its chain homotopy equivalent to this model, which is like a derived tensor product of two algebraic invariants, one CF d hat of S3 minus nu of k is some type D structure over an algebra associated to the torus. And on the left here, we have CFA hat of S1 times D2 relative to the pattern. This is an A infinity module over the algebra associated to the torus. And to reconstruct the invariant of the satellite knot, I take and I combine these in a suitable way. This suitable combination involves a lot of algebraic calculations. So I want to talk about a geometric reformulation of this pairing theorem for 1-1 patterns. First, I want to mention the work of Hanselman, Rasmussen, and Watson in realizing CFD hat as some geometrically defined object. So their work from 2018 says you can take CFD hat of a knot complement, any three manifold with torus boundary actually, and you can construct an immersed multi-curve in the punctured torus. So on the right here, I have an example of an immersed multi-curve for the trefoil complement as drawn in the punctured torus. The base point W is up in the top right corner, and these red arcs are the immersed curve. A way to see that sort of in a different way is to lift that picture to the universal cover, and that's what I've drawn down here in the bottom left. This here is a lift of that curve to R2 minus the lift of the base points. And you can see, at least here, if I pair this curve with a vertical line, I'll get three generators. And I claim that those three generators are in correspondence with the generators of H of K hat of the trefoil knot that we saw in the previous talk. This has Alexander grading 1, Alexander grading 0, and Alexander grading -1. Which is I'm just recording the height at which that curve crosses and intersects with the blue vertical line. Another example of an immersed curve associated to a knot is the one in the middle here, and this is the curve associated to the figure 8 knot. Notice here it has two components. One of the components is contained in a neighborhood of the base points, and is this figure 8-like component, and it's honestly an immersed curve. And the other component is horizontal. That component is the component I'll call gamma 0. And I'll call that the essential component of the immersed multi-curve. The essential component of the immersed multi-curve is the unique component of this collection of immersed curves in the torus that is not contained in the neighborhood of the base points when I lift it to the universal cover. And its behavior, its shape, is determined by two auxiliary invariants you can associate to the knot Floer homology of a knot, namely tau and epsilon. So tau we discussed in the previous talk, and I claim, so here on the left is an example of the general picture of the immersed multi-curve when tau of k is positive. The point here is that it crosses through the lift of the base point at height tau of k, and at height minus tau of k over here. It slopes positive. And then its behavior right after it crosses through that neighborhood of the lifts of the base points is determined by epsilon. So the case where the curve is dotted here, that's epsilon of k equals 1. And the case where it's not, it's solid, that's epsilon of k equals -1. So if I know tau and epsilon, I know partially the shape of this immersed multi-curve, at least how it looks outside of a neighborhood of lift of the base points. And from work of Hanselman, Rasmussen, Watson, they show that any other component of the immersed curve is contained in a neighborhood of the base points. So it's localized here. Similarly, you can see, I'll show you in this case on the right, this is the general picture for tau of k less than 0. Here it crosses at height tau of k and minus tau of k. And again, whether or not it's solid or dotted depends on whether or not epsilon is plus or minus 1. Okay. That gives us some indication of the form that these immersed multi-curves take. Let me move on and discuss CFA hat. So CFA hat, in general, it requires a computation that sort of is case by case, that depends on the pattern. But there's a really nice family of patterns where you can actually reformulate this pairing theorem in terms of just a simple geometric picture. And so that's the class of patterns with a genus 1 doubly pointed bordered Haggard diagram. So let me try to describe what those are right now. It's a 5-tuple of data, sigma, alpha arc, beta, W, and Z, where the sigma is a genus 1 surface with one boundary component, and I've drawn that on the left. The alpha arcs, for us, we can just think about them as copies of the meridian and the longitude. So the alpha 1 arc is the longitude, and I've drawn that here horizontally in red, and the alpha 2 arc is the meridian. I've drawn that vertically in red. The beta curve is just a simple closed curve in the interior of my surface sigma, and I've drawn that here in blue. I'll call that beta of P. And then I choose 2 base points in the complement of the alpha arcs in the beta curve. Here's W and here's Z. And I choose them in such a way that when I forget the Z base point, the beta curve is isotopic to the meridian. Okay. And once I have this 5-tuple of data, it defines a 3-manifold with torus boundary and a knot inside of that 3-manifold by the following recipe. I take sigma cross I thicken up the surface, and I attach a 2-handle along the beta curve. And then to recover the knot, I connect Z to W in the complement of the beta curve. And then I connect W to Z in the complement of the alpha arcs. You can see that this would be a doubly pointed genus 1 bordered Haggard diagram for the 3-1 cabling pattern. Okay. So once I have a genus 1 doubly pointed bordered Haggard diagram, Wenjiao Chen's pairing theorem from 2019 says that, well, I can compute the knot-Floer complex associated to the satellite knot with that pattern by computing the Lagrangian intersection Floer homology of the curve alpha of K, which was the immersed multi-curve defined by Hanselman, Rasmussen, and Watson, associated to a knot complement, with the beta curve from my genus 1 doubly pointed bordered Haggard diagram. And I do that in the following way. I take the torus, and I divide it up into 4 quadrants, and I put the alpha curve in the first quadrant, and I put the beta curve in the third quadrant, and I extend those curves into the second and fourth quadrant where they will intersect in some number of points. And those intersection points, those are the generators of this Lagrangian intersection Floer chain complex. So they occur in the second and fourth quadrant. And the differential on this complex, it counts bigons that don't contain either base point. And so it's here, it's the mod 2, the differential of x is the sum over all y, where they weight that generator by the mod 2 count of bigons from x to y. And these bigons come with some kind of direction in the sense that bigon from x to y looks like this. It has the beta curve on its left and the alpha curve on its right. So this would be a contribution to the differential of x, and it would show that y shows up at least once in the differential of x. For a concrete example, over here, I've again drawn the alpha curve associated to the 2,3 torus knot. And I've drawn a beta curve associated to some pattern that we'll see later. In the second quadrant, I have 9 intersection points, and in the fourth quadrant, I have some number of intersection points. And those are the generators of the Lagrangian Floer chain complex. I've indicated 2 differentials. One goes from x0 c0 to y0 mu1. That's the light shaded bigon. And the darker shaded bigon goes from x0 c1 to y0 kappa. And so the work in Chen's theorem is showing that derived tensor product has a model in the case where P has a 1-1 pattern that's just given by Lagrangian intersection Floer homology in this twice punctured torus. So my 2 punctures are again the 2 base points from the doubly pointed bordered Heegard diagram for the pattern. Not only does it give us a concrete description of the generators, actually also gives us a way to compute the Alexander grading difference between 2 intersection points, which corresponds to generators in this chain complex. And I can do that by picking an arc on the beta curve that goes from x to y, and picking an arc that goes from w to z, and I compute the intersection, algebraic intersection between those 2 arcs. So for example, here, you could look at the generator x and the generator y, and if I connect them by walking along the arc of the beta curve from x to y, I cross the delta wz arc here once algebraically. And so the Alexander grading of y minus the Alexander grading of x is equal to 1. So this is wonderful because we really wanted a way to access not only the knot Floer groups of a satellite knot, but the Alexander grading filtration as well to get apply these detection results that we mentioned in the previous talk. So let me show an example of how to do that. Here's a pairing diagram. I've drawn it now lifted to the universal cover minus the pre-images of the W and Z base points. Here's W and Z, W and Z, W and Z, W, Z, etc. And I claim that the beta curve, the blue curve here, that's the beta curve associated to a genus 1 doubly pointed bordered Heegard diagram for the measure pattern, Q, that we discussed in the previous talk. Remember that there was some work of Ina showing when the n-twisted measure pattern is fibered. I want to show you here that you can reconstruct that calculation using the immersed curve picture here of Chen. So by the description of the Alexander grading difference of 2 generators, you can convince yourself that the Alexander grading of A and the Alexander grading of B differ from the Alexander grading of X here, which is the central intersection point, by 2. So once we can also convince ourselves using some symmetry properties of the knot Floer complex that the Alexander grading of X is 0. And so that actually tells us that the Alexander grading of A is the Alexander grading of B is 2. If you stare at this picture a little bit, you'll see that that's the largest possible Alexander grading of any intersection point. And so by the genus detection of knot Floer homology, that's going to be the genus of this satellite knot. And so we see, recovering Ina's result, that the zero twisted measure pattern is never fibered for any, that if I apply that to any fibered knot, I'll never get a fibered knot, so it means that that pattern is not fibered. And we see that again by seeing that the rank of the knot Floer homology in topmost Alexander grading is 2. Just for another example of how this works, here's the one twisted measure pattern satellite, again applied to the 2-3 torus knot. A computation shows that the Alexander grading of A is equal to 3, and it's not too hard to see that there are no other intersection points in this Alexander grading. And so the genus of this satellite knot is 3, and this satellite knot is fibered, which also recovers the fact that Ina showed that the one twisted measure pattern is always fibered. Great. So I mentioned in the previous talk that Chen used this theorem to compute tau of satellite knots where the pattern, if I included it into 3 sphere, it would be isotopic to the unknot. I want to present here a construction for producing a pattern with a doubly pointed genus 1 bordered Hagar diagram so that the knot type of the pattern in S3 is the trefoil knot. So here's an infinite family of such patterns. Start with the P1 cabling pattern. Here I've shown the 3-1 cable pattern. I want to take that pattern and I want to do a finger move on this bottommost horizontal strand here. So I'm going to take this strand and I'm just going to push it once over the longitude. When I do that, I introduce 2 more intersection points between the beta curve and the longitude. And then I'm just going to continue tracing around and following the pattern here. So let me redraw it to give myself a little bit more space. I'm going to go through here and I'll push it until I end up inside the bygone that contained the Z base point, and then I'll just hook it over the Z base point once. And I end up with this beta curve on the right. And you can see that the dimension of the knot Floer homology of this pattern applied to the unknot is 3. And since knot Floer homology detects the trefoil knot, I don't even need to draw the actual knot I get in S3 from this construction. Know that when I apply this pattern to the unknot, I get the trefoil. Okay. It's also easy to see that this generalizes, and so I have a piece of P1, a pattern of this type derived from the P1 cabling pattern for every P bigger than 1. And if I apply that pattern to the unknot, I'll get the trefoil knot, because in this construction, I've only introduced 2 extra intersection points with the longitude, which will just give me 2 extra generators in the knot Floer complex of that pattern associated to the unknot. Okay, so this gives me an infinite family of what I'll call trefoil patterns. And here's the result. It says that for each P bigger than 1, there's one of these patterns with knot type of the trefoil in S3. It has winding number P plus 1. It has genus 1, and it's fibered. And furthermore, you can actually compute tau of K, tau of a satellite, P sub P1 of K, in terms of tau of the companion and epsilon of the companion. This follows from the description of the essential curve component for CFD hat of a knot complement in terms of tau and epsilon that I mentioned. Okay. Furthermore, since you know that these are fibered, you might ask, what about the next to top Alexander grading, which, as we saw in the previous talk, somehow detects whether or not the monodromy is left or right veering. And you can show using a structure theorem for thin knots that if I have a thin fibered knot, the satellite I get using this pattern always has left or right veering monodromy. This is similar to the computations we did above showing that the measure patterns are fibered. It's just analyzing the next to top Alexander grading and seeing that there's only one intersection point that can realize that Alexander grading. A corollary of this that is interesting, I think, says that if I have a fibered thin knot, and I happen to know that tau of that knot K is strictly less than G in absolute value, then I can show that the knot Floer homology of the satellite knot P sub P1 is not thin. Where by thin, I mean the following. So there's a collapsed delta grading on knot Floer homology that I get by just taking the difference in the Maslov and the Alexander grading. And a knot is thin if for all generators, the delta grading is constant. So let me just mention how to prove this corollary. It relies on this recent result of Baldwin, Nie, and Seebeck that says that for thin knots with tau of K in absolute value less than G, that knot, if it's fibered, it can't have right or left veering monodromy. So I should say if K is fibered, then and absolute value of tau of K is less than G, K does not have left or right veering monodromy. So we can use our tau computation from above of these satellite knots to see that whenever tau of K in absolute value is strictly less than G, the same is true for the satellite knot. And so since these knots have left or right veering monodromy, they can't be thin. Right. In the remaining few seconds, let me mention how to prove some of these results. So here's a pairing diagram that computes the knot Floer homology of P sub 3,1 of the right-handed trefoil knot. The picture is very similar for P sub P1 for any P bigger than 1. It's not hard to convince yourself that as I walk down this diagram along the beta curve, so as I walk along this arc, I'm always intersecting the delta WZ arcs positively. And so the Alexander grading is weakly decreasing as I go down the diagram. And so the Alexander grading of A will be the largest Alexander grading. And again, by symmetry, we can see that the Alexander grading of X is 0. So we can just compute the Alexander grading difference between A and X and see, in this case, we get the number 5. And so that allows us to compute the genus of this pattern. And we get in general, we'll see that the genus of P sub P1 is 1, as claimed. And furthermore, you can see that the next to top, the next possible largest generator with any Alexander grading here is B, and that necessarily has Alexander grading of A minus 1, because we have to cross one delta WZ arc to get from A to B. And so we see that A is the only intersection point in Alexander grading 5. And so by the detection of fibered knots, P sub 3,1, or more generally, P sub P1 is fibered. And so this P sub P1 is a fibered pattern for every P. There's also work of Chen that says that in this pairing diagram, we can compute tau by considering bigons that cover just the Z base point. And these are going to correspond exactly to differentials in the spectral sequence we discussed from knot Floer homology to the Higard Floer homology of S3. And carefully staring at this picture, you can convince yourself that, for example, if tau of K is positive, and epsilon of K is equal to 1, which is what's going on in this picture, for example, the right-handed trefoil, that tau of P sub P1 of K is P sub 1, P plus 1 times tau of K plus 1. Thanks everybody for listening. I should stop. I'm excited to meet everybody in office hours and interact with everybody as this conference goes on. Thanks again for listening.